Um, yeah, so it's the Thanksgiving week, but really glad to see so many people still coming. It's my great pleasure to introduce our speaker today, Professor Xiaohui Fan, from University of Arizona. So Xiaohui was a professor in University of Arizona and Stewart Observatory, and was associate head of the department for a long time. And he is famous for his search for the first luminous quasars with survey data, and studying history of reionization, black hole galaxy evolution. Xiaohui did his PhD long ago, more than 20 years here in Princeton, and then moved to IAS for 2 years as a member, and then joined Arizona. So he was among the first people working on SDSS survey, and he said even building the survey himself. Xiaohui won several awards during his long career, and was is among one of the Thomson Reuters highly cited researcher. So today, Xiaohui will tell us something new about quasars with JWST data. Let's welcome him.
All right. Hear me okay? All right. So yeah, thanks for that introduction. It's great to be back. Thanks for hosting us here this semester. We're enjoying our staying here to both reconnect and to start something new. So today I'm going to show you some of the new JWST results on the studies of quasars at the epoch of reionization, a cosmic dawn, both of the quasars about their environment, with a collaboration that we call the Erebus collaboration, picture here that I'm going to choose a little bit later. I believe with those data, we're finally begin to put high-redshift quasars in the context of the physics of black hole growth, galaxy formation, large structure, and reionization, and begin to answer the question of whether big black holes or massive galaxies appear first in the universe. But of course, the study of quasars at epoch of reionization really started right here in Princeton, when almost 25 years ago, we started following up these red objects from the Sloan Digital Sky Thermal Imaging, which I think these days we should call them the original little red dots. They are either quasars or brown dwarfs, or God forbid, Robert's favorite object, cosmic rays. And we were starting to follow them up. This is an observing log from 2002 that Michael and I were observing the basement of Peyton Hole using the APO 3.5 meter. And we found this object, which we immediately recognized was a quasar redshift 6.4, which would be, at that time, the highest redshift object known. And we immediately called up Jim Gunn, I think, in the middle of the night, tell him that. This was, for the quasar aficionados, the object SDSS 1148, which for a number of years was the most distant quasar, also probably one of the best studied objects at high redshift, because this object is extremely bright. And you can see from this better Keck spectrum, there are these deep absorption troughs that Jim have told us about since 1965. These are the Gaussian absorption troughs that tells you that at those redshifts, finally, the universe intergalactic medium was beginning to be opaque to MR photons as the neutral fraction of hydrogen is increasing in IgM. So this marks sort of we're entering to the epoch of reionization. So that's the start. And a few years later, we sort of wrote a review article to try to summarize what we learned from SDS quasars about reionization and such. And this was a figure from the review article, which basically showed all the SDSS redshift 6 spectra, quasar spectra, in one plot. There are about 20 of them or so. That's all we had at that point. Since then, the community has built on the SDSS and expanding to other imaging surveys with large area, with more depth, and also especially towards redder wavelengths, allow us to build up a very large sample of quasars now. There are about more than 1,000 quasars known at redshift higher than 5, more than 200 at higher than 6, and about 10 of them at redshift higher than 7 also, with the highest redshift now for luminous quasars at redshift 7.6. So a couple of years ago, Eduardo Donados, Rob Simcoe, and I decided we're going to write another review article to basically summarize what we know about these quasars before JWST launch, because we know quickly this knowledge is going to be obsolete. So we want to sort of just have a benchmark of what we know about quasars. So because of this plot become actually quite popular, as it sort of summarizes what the quasar spectra look like at reionization era quite nicely, we want to remake this plot with all the new quasars to show what it looked like. It didn't quite work. So we put them in this two-dimensional rendition, which basically stack all the spectra and have this two-dimensional composite of spectra. Of course, you see the Lambda alpha line now extend to more than 1 micron now. So the UV radiation transition finally become a real infrared line at redshift higher than 7 also. On the blue side, again, the deep complete absorption indicating the reionization is setting in. And then when you go to some lower redshift, you can see carefully there are transmissions again when you go to redshift lower than about 5.5 also, as the universe is getting out of reionization and the ionization front is sort of conquering the last remaining neutral island of the IGM. I'm not going to talk more about reionization in this talk. I'm going to show a few things about what's new with reionization at lunch. Today, I'm going to focus on this part of the spectrum, Lambda alpha, and you can also see these strong, broad emission lines that you're familiar with in the quasar spectra, silicon-4, carbon-4, so on, continue to be very strong, even when you go to the highest possible redshift. Well, that tells you that chemical enrichment, at least in the quasar vicinity, occurred extremely rapidly in early universe. And of course, that really is starting to connect the growth of supermassive black holes in these quasars with the environment, with the galaxy environment that quasars are living in. So that's really the topic of today's talk. And I think some of the earlier questions about this area was asked really going back to this old review paper, Martin Rees, almost 50 years ago now, where it's basically asked two questions. One is, what is the pathway from the earliest collapse of baryons to the massive black holes that we see in the center of quasar? Whether it's through sort of Eddington limit accretion from normal stellar collapse, or whether more exotic channels and pathways are needed. And we'll try to answer the question a little bit and actually really show the limitation of how much we can answer it a little bit later. And the other is to put quasars in the context of entire galaxy formation and growth of lattice structure. And I think center to a lot of these things, as summarized in this diagram from Matteo Monteri, is that how do you get from the early quasars we observe to the local galaxies that we see the strong scaling relation between the black holes and their host galaxies, whether they are sort of go hand in hand, whether black holes grow first and galaxies catch up, or whether there's rapid galaxy assembly and then black holes accrete later. And I think probably by the end of the talk, you'll not be surprised if I say that the real picture is complicated. There are different pathways of reaching towards that. But I think it's a process of trying to understand what is going on in these pathways that's teaching us a lot about quasar physics and their connection to galaxies. So one thing I really like about quasars is the range of physical scales they're probing, all the way from very close to the main horizon of the black hole and the accretion disk, where, of course, you're trying to understand the seed of the black holes and how they accrete. Few order magnitude larger scale, at the galaxy scale, we're trying to look for the signs of whether quasars are impacting their galaxy evolution through feedback. And yet another few order magnitude larger at the megaparsec or tens of megaparsec scale, quasars could be anchoring the earliest structure formation in the universe. And of course, they're probing cosmic reionization as well. I'm going to talk a little bit about all these three scales in today's talk, starting with sort of the small scale, the accretion part. So this is a spectrum of the most distant, I will call it luminous quasars in this talk, just to distinguish them with a lot of the AGNs that people are studying with JWST these days at even higher redshift. These are sort of the SDSS-like quasars, the things that you associate with type 1 objects, look like 3C273. So the most distant luminous quasar today is a redshift 7.64. This one was discovered a few years back now. Actually, it was the very last observing run that we had on Magellan Telescope before pandemic. We didn't know that. It was the last object we could observe that run, and we're lucky because we didn't get back to the mountain for another 3 years. So this is a redshift 7.6 quasar selected through different optical imaging selections. I want to point out two interesting features of this spectrum. This is a magnesium-2 emission line of the quasar. We use this to measure or to estimate the black hole mass. And the way to do that is, since this broad line region is well within the sphere influence of the black hole, where the black hole gravity dominates, we can regard the line width of this object to be sort of the gravitational velocity. So you have v squared there. And then the size of the broad line region can be scaled roughly to luminosity to the square root of luminosity, sort of just photon ionization. And the scaling relation is established by low redshift optics through so-called reverberation mapping method. So now you have v squared r, you get a black hole mass, in this case, turned out to be a little bit more than 1 billion solar masses. So that tells you 1 billion solar mass black hole existed at redshift 7.5 at about 700 million years after the Big Bang. So that's the first message. The second are these features. These are strong broad absorption features. Turned out to be quite common among these very high redshift quasars. These are carbon-4 and silicon-4 absorption, redshift, blue shifted to 0.1 to 0.2 speed of light. That tells you these quasar accretion are driving very rapid winds. We do not quite know where these winds are, but they clearly have the energy and velocity that could do damage to the galaxy formation. And we'll come back to look at a better tracer of this wind when we can spatially resolve it later. So that's of course one quasar, and now we have a lot of spectra from these objects, from ground-based basically infrared spectroscopy to measure the black hole mass of these objects. And this is the black hole mass of the collection of objects we had at redshift 7.0, so you can see the range is sort of between 10 to the 8 to 10 to the 9 solar masses. There's one more object that we thought maybe even more massive, a 10 to the 10 solar mass, at redshift a little beyond 7, which we're using JWST to try to get a better black hole mass measurement right now. So again, 10 to the 9 to 10 to the 10 solar mass already existed at that time. And you plot them on the black hole mass versus luminosity plane. This is your Eddington limit as a function of black hole mass. These things sort of pile up along the Eddington limit line. So these things are really accreting about as fast as, there's no assumption made about whether they're Eddington or not. They're just from measurement of black hole mass and luminosity, they are accreting about as fast as they can, compared to lower redshift sample where centered somewhat lower Eddington ratio. These are low redshift SDSS quasars.
But that's just a selection effect when it's sensitive to the most luminous objects at any given.
I mean, these are more or less, yeah, sure. But even if you do luminosity matched sample, it still have the same trend, I believe. But anyway, so at least for these quasars, they are at high redshift with a high black hole mass and accreting at the maximum rate. Now, of course, people all made this point many times. If you combine the two, then you get a picture of in order to get 10 to the 10 solar mass at redshift 7, and just assuming that they're continually accreting the Eddington and 100% duty cycle, so you're doubling the black hole mass every 30 million years or so, you require, even if it's on a collapse at redshift 30, for the seed black hole, you require them to be 10 to the 3 to 10 to the 5 solar mass seed. That was the standard argument people use. And I think this argument is still relevant in the sense that the only real observation we have about seed black hole that we know are collapse of massive stars. And the evidence is that these quasars do accrete at sort of Eddington-ish luminosity. So this may not be completely crazy, but on the other hand, there are many other pathways. People all like talk about direct collapse black holes or things that accreting more efficiently through supermassive accretion. These things are the things that we really have to look for to see whether this works, whether you really need direct collapse. And I would argue that for two things. One is these objects that we observe are the most extreme ones, as Michael said, and they're not representative of the entire population. So maybe these objects are just special, and we don't understand how special they are. And of course, when you go to somewhat lower redshift, 4 or 5, then this timescale argument becomes much easier to deal with at that point. The second is these are 10 to the 9, 10 to the 10 solar mass. It's about as massive as any black hole that you observe in the local universe. It's basically M87 kind of thing. And so what that means is these things are not going to grow very much anymore. So we're looking at the end product. So in order to really understand this, you really need to go to lower mass, higher redshift to capture the intermediate process between the end product and the beginning. And I think that, of course, is what exactly JWST is doing. Yes, Jeremy?
Radiative efficiency is assumed in those
Just standard 0.1-ish. So of course, everything scale with the radiant efficiency. Yeah. Yes. Right. Yeah.
I have a question on that plot before, which is the argument about where these had to start at the left edge depends on just how far left you go in redshift.
Well, that's 30 now. They're not much more.
But how do we know what's the right redshift to start?
What? I'm sorry?
How do we know what's the right redshift to start the math?
Well, I guess we'll try to find out what. But I guess the series will tell you that start at redshift 30 or 50. Of course, again, these are extremely rare objects, so maybe they are special, right? Yeah.
The upper axis is the relevant one. There's not much more time.
Yeah, it's a time limit. That the time is extremely compressed at redshift 30. You don't have a lot of e-folding, whatever you do at that point, right? So of course, that's what the story little red dot. I'm not going to talk about it little red dot today. We do have little red dot from our own JWST data as well. I think Andy actually is going to say a little bit more about little red dots today in lunch, except to say that these are the things we really should study to understand the earlier phase of black holes that grows at lower mass, extremely high redshift. All right, before we go to talk about galaxies around quasars, one more thing is that I worry about the black hole mass because these are based on these scaling relations that are calibrated on much lower mass and lower redshift objects. Do you know really do they really work at those redshift? It turns out finally we are getting close to be possible to actually do dynamical mass measurement rather than the scaling. And this is an example of a really neat system that we discovered a few years back. It was a triply lensed quasar at redshift 6.5. Because of the strange configuration of lenses, of a lensing system, this object actually magnified a factor of 50. So in optical wavelength. So it's actually the brightest object at the high redshift at almost entire wavelength range. It's very bright in optical, infrared, submillimeter, and everything. That allow you to do very high signal noise observation at even the highest resolution. And of course, because of the lensing magnification, you get extra boost on the spatial resolution as well. So we actually can resolve this object at a spatial scale about 50 parsec at redshift 7. And that's just a lot. And the sphere influence of this black hole is probably of the order of 100 parsec. So we sort of begin to barely resolve the sphere of influence for this particular object and begin to ask what the black hole is doing dynamically in this system. The lensing model is a mess, so I still do not have, after a couple of years, still do not have a rotation curve, except to say that in the center part of this is probably the size of sphere of influence. You do see a very strong velocity share of a couple hundred kilometers per second. Sort of the things you want when there is a very massive object that's causing the rotation there. So stay tuned when we finally are happy to show what the dynamical measurements is. Yeah, you can with a bigger scale. I mean, we're not confident to revert the lensing map within the center, but in a bigger scale, you'll see a very nice rotation curve. Actually, I don't have a plot to show it, but very nice few hundred kilometers rotation when you go to beyond like 1 kiloparsec also. So that velocity, that's the reddest part is like 200, and always in a very small region. So it's sort of interesting. All right, so that's about the quasars themselves. We can move on to the larger scale about galaxies around quasars. So when we think about quasar host galaxy, the first thing come to mind are these beautiful pictures from, of course, John Bacall and his group's work 3 decades ago using HST to look at low redshift quasar host galaxies, see a diversity of hosts from elliptic looking to spiral to interacting system. We would love to see them in high redshift, but turns out to be really hard with HST even. When you go to redshift 6, things are just too faint, too low, surface range is too low, and quasars are too bright. Of course, that's where really JWST power comes in, because of the sensitivity, because of the resolution, and really because you can reach to the resonant optical wavelengths or the observed mid-infrared wavelengths, where the contrast between the quasar and their host galaxy is much more favorable. So that's what we're trying to do, sort of starting with our JWST program. So now I'm going to introduce the collaboration that we have called Erebus, stand for reionization, black hole, and something else. As you know, Erebus is the primordial god of darkness in ancient Greek. So we thought it's a good acronym for like black holes and dark ages and that kind of stuff. It's really a JWST in ALMA survey of a fairly large sample of luminous quasars at reionization epoch. So these are some of the targets. And the goal is to tie really tie the galaxy, high-redshift quasars in contact galaxy evolution and reionization. And these are just a number of different places we went to for our international collaboration meeting. So this particular program or collaboration is anchored by two sort of large-ish cycle 1 JWST programs with cycle 2 and cycle 3 follow-up to sort of supplement it. The first of the cycle 1 program was called Aspire. The acronym is even worse. I don't really remember how they did it, but it was doing 25 quasar redshift about 7 with one single mode, which is basically near-cam slit spectroscopy and imaging. So instead of doing slit spectroscopy, we're opening up the entire field, so every object become a spectrum. So in addition to the quasar, you have all the galaxies in the field have spectra as well, whether it's in the foreground and the quasar redshift in the background, to understand both the quasar and the environment. Of course, key here, we do 25 pointings to get a sense of statistics. So that's the first one. The second project is sort of the other approach. Instead of doing 25 in one mode, we're doing 3 quasars in every mode. So these are the 3 highest redshift 7.5 quasars. We essentially use all the modes that we have access to try to get sort of the entire coverage of the quasar from 1 to 20, 25 micron with both spectroscopy imaging and integral field spectroscopy to try to understand as much as they can to build them as sort of a prototype high-redshift quasars for the future surveys. So I'm going to combine these two programs in the follow-up program, just show you the highlight of what we find so far. First, we'll start with just the spectra themselves. All these quasars are nice spectra. And we are zooming in on the redshift optical region for various reasons. This is the H-beta oxygen 3 region of the sort of one of the redshift 7 quasars with a broad H-beta line and narrower oxygen 3 line. Of course, the thing we want to observe H-beta is because that's sort of the standard calibrator for black hole mass of these objects because they're better calibrated locally. And so we want to at least first confirm whether the black hole mass we get from magnesium-2 and other lines are reliable because we don't have access to H-beta until JWST really for these redshift. They are more or less consistent. The black hole mass from H-beta and magnesium-2 are more or less consistent. If anything, maybe there's a slight trend of the H-beta mass a little bit lower. This is an entire, actually combine those two, there's an entire spectrum of two of the redshift 7.5 quasar, go all the way from lemma alpha at 1 micron to H alpha at 5 micron, in this case from H alpha all the way to Pershing alpha at almost 20 micron now. So you have the whole range of spectra of the single object. And when you go to 20 micron beyond, or 10 micron beyond, these are the red frame near infrared now. So you begin to see the hot dust. So certainly the hot dust torus is there, still at those highest redshift. This is an insert is an IFU spectrum of the oxygen 3 line, which we'll talk about later. So that's the spectrum we're working with. On the imaging side, we all have imaging of these objects well. This is begin to look like what John Bacall's gallery of quasar host galaxy look like at low redshift. They show a very wide range of morphology and sizes. Some of these are all redshift 7 quasars from like JWST. These are all red frame optical, sort of a 3-4 micron imaging. Some of them are very extended, like up to about 10 kiloparsec size of those redshift. You would expect higher redshift galaxy to be more compact. Some of them are actually quite big. Many of them show merger features that have close companions, interactions, and so on. So good fraction of them are interacting systems. Some of them are fairly isolated that have sort of exponential looking light profiles that's consistent with this. And some of them actually have Elmo observation. I'll show you one of them in the next slide that show a disk looking like kinematics. And still about 1/3 of them are not detected in the sense that after PSF subtraction from the JWST, we still do not see the stellar light from the quasar. They are either too compact, too faint, or too densely obscured, or a combination of the three. So we do see a very wide diversity of property of host galaxies. The other message is that the property of host galaxies don't seem to correlate with any particular black hole property, whether black hole mass accretion. Of course, we don't have a lot of dynamical range quite yet, but at least by looking at the black hole themselves, you cannot predict what kind of host galaxy they're living in. So that's sort of interesting. They don't seem to know each other particularly well. Yes?
This is still a continuum. It's not, you're not at an emission line.
Yeah, these are all continuum images. Yeah. So these are our three sort of the poster child good example, an example of impressive massive galaxy hosts. The first one is JWST image. Look like a train wreck, a lot of stuff going on. Both JWST and we'll show also ALMA observation, the same system with a lot of the same companions with C+ emission line detections. And this object also turned out to be in the middle of one of the massive protoclusters or large protocluster we have at high redshift. Almost made me feel like this is some kind of very early version of the brightest cluster galaxy at redshift 7. This is a clear merger. There are just two things going next to each other and have sort of a bridges between the two. The third one is one of the largest galaxies we have. That's JWST. That's ALMA. The ALMA observation has a fairly large round-looking structure with a very, very strong velocity share on top of it. It's a couple 100 kilometers per second. This is more or less phase on. I'm not going to quote a dynamical mass just because I don't quite know the inclination, but the dynamical mass is going to be large. It's going to be 10 to 11 or more for internal dynamical mass. One of the more massive systems that we have. So these are three examples, clear example of some of these systems are in massive quasars in massive galaxies that are being put together. So this, I believe this is a continuum. This is a C+ velocity field. Yeah, I think all these three are continuum. All these three are C+ on the same system. All right, so now we have stellar light. We have some of them have even sort of a velocity information. We can measure mass. So this is our preliminary result on the stellar mass. We don't have a lot of bands, so take whatever you want about how accurate the SED fitting is to get a stellar mass. But overall, the mass of these systems are 10 to the 11-ish, which compared to the black hole mass of 10 to the 9 to 10 to the 10-ish, you can see the ratio is high in terms of the black hole mass fraction, which is older magnitude or more higher than local relation. People have been consistently finding that essentially the black hole, the host galaxy, even though there are some of them bright, are not quite as bright as you want them to be. Otherwise, they would have been detected by JWST a long time ago, I think. But of course, that's not the whole story. I mean, like, I think Todd Lauer was the first person who pointed out that there has to be some very strong luminosity bias in the sense that we're looking at the most extreme system. If you have intrinsic scatter, then you're going to, and we're selecting on quasars, we're selecting by flux, you're going to pick up these systems. I think that's when we try to actually put them into some cinematic modeling to figure out our selection effect. That's certainly very, very large part of the story. And indeed, when you go to look for, these are the fainter quasars on the HSC survey that have JWST observations, they are closer to the local sort of black hole mass, stellar mass relation. What I view this is that there's no relation. They don't quite know each other, that you do not have a very strong trend between black hole mass and galaxy mass, except maybe there's some sort of thought, I don't know whether there's an upper envelope, but it's still very impressive that somehow 10% of the stellar mass end up in the black hole in the solar system. Andy?
Say stellar mass in this case, do you mean of the entire system, like the one where you're saying like a broken BCG?
Just a central. I think that just a central galaxy, whatever the host galaxy, the central component of the host galaxy is.
Black hole mass here is dynamical measurement, or
the black hole mass are the black hole mass from the spectra that I showed earlier from H beta or magnesium 2. The stellar mass just fitting SED from the JWST multiband imaging. So my take is there's not much of a relation except quasars probably have taken different route to get there. The same story with ALMA. So ALMA, you can do sort of a dynamical analysis because it's basically an IFU of the gas, right? So the thing we use are the C+ line, the strongest line that ALMA can do. They again show very large diversity of the morphology. Some of them look disky with like velocity, just almost like a nice butterfly diagram. Some of them are dispersion dominant, and the 1/3 of them are sort of disturbed. So if we get rid of the merging system and try to estimate the dynamical mass from these maps, you get the same message. They don't seem to have a relation, but they seem to be all not very high in terms of dynamic mass compared to the black hole mass and calibrated local relation. Yeah.
Distribution of Eddington factors.
In this one?
In the previous plot.
No.
For the ones in the upper ellipse, are those
So
Eddington ratios?
they're all close to 1. Yes.
Even the
The faint ones are not necessarily. I think Michael knows better. They are lower. Yes. Oh yeah, that's the point. Yeah. Yeah, I think my main message is I don't think there's a relation, and we do, but except I see scatter. I see the, yeah. I mean, things with very different black hole mass. I guess things with very different black hole mass can end up with very similar false galaxy mass at this redshift. So these are the ALMA observations, which of course have very different systematics, but sort of similar mathematics.
Curious if you have this, say, more direct observational plot of black hole luminosity versus stellar luminosity? Because I think getting massive.
Sure. Yeah, we certainly do the Lagrangian kind of thing. Yeah.
Is there,
I don't have a plot showing that, but we should do that. Thank you. All right. So I think that's about host galaxy. But of course, from the starting point of this kind of M-stream kind of relation, immediately people 20-some years ago begin to say this must be some kind of feedback that make black holes and galaxies know each other. And of course, when both Phil Hopkins and I were younger, he began to tell us quasar mode feedback must be very powerful and blow up gas around them. Turned out to be, I mean, that picture was nice, but when you go to lower redshift, it turns out it's not easy to find the evidence of these full-blowing quasar feedbacks that allow him to blow up the entire ISM and end up with a neat picture of early galaxies. So real picture, at least the low res, seems to be much more complex, I think. Now we can do that in high redshift to actually look at the gas ISM gas in those galaxies. Particularly, we can look at oxygen street, which usually is the strongest nebula line in an ISM, and you can try to look at spatially resolved information oxygen street to see whether it's the outflow or not. So this is our first attempt, is a JWST IFU observation of redshift 7.5 quasar at H-beta oxygen region. The first thing I want to tell you is the insanely high signal noise of these spectra. These wiggles are real. They are not noise. They are like just tiny iron 2 emissions that are blended together. You can fit them. And it's a not very strong oxygen stream in a particular object. But when you try to get rid of the central PSF, you will see the oxygen stream is spatially extended to a couple of kiloparsecs with fairly high velocity of up to about 1,000 kilometers per second. So you're seeing sort of a one-side outflow. And you can try to estimate what the kinetic energy that is associated with this outflow. There's a study where people doing it has all kinds of assumptions into it, but you can combine the luminosity, the size of the outflow, the velocity, with some assumption on the clumping factor, some assumption of the density of the things and metallicity and everything. And you can get a kinetic energy of the outflow. Again, these are probably order of magnitude estimate, but it's good to compare them, these objects, with low redshift observations. In this particular case, we do see a strong outflow with very high velocity, probably driven by the quasar, but the energy is not that high. It's a fairly modest outflow for this particular object that we have the deepest observations. Otherwise, we probably would not see it. And now we have actually a few dozen of these things that we can look at their oxygen stream information a lot in a statistical way. I think one thing when I give quasar talks, I like to say, and a lot of people like to say, is quasar don't seem to care about redshift. They don't seem to change very little from redshift 0 to redshift 7. That's probably wrong, at least in some sense. This is the SDS's sort of standard oxygen stream H-beta region. You have the broad H-beta line. You have the narrow few hundred kilometer oxygen stream forbidden line from the narrow line region that was supposed, what quasar is supposed to look like. This is not a typical low redshift quasar. This is a redshift 6 quasar, which H-beta, and then oxygen streams are extremely broad and have a very strong blue wing outflow again. And if you look at where the blue wing comes from, this is a 2-dimensional spectrum. You see the things stick out. So these are spatially offset and velocity offset as well, outflow from the oxygen stream. That is where the blue wing comes from. For a couple of kiloparsec, few thousand kilometers per second wind coming from the quasar. If this object is restrained, this is worse. So this is H-beta oxygen. It doesn't look like anything. This looks like just 3 fat lines blended together. If you try to deblend it, the wing of the oxygen stream get all the way to close to 10,000 kilometers per second. This is about the most extreme object we have at redshift 5 or so. So we don't see these things very often in local universe. If we want to try to do the statistics, so we begin to put together a lot of the IFU observations of these quasars. this kind of few thousand kilometers per second outflow is actually quite common. They appear to be they're not actually terribly deep observations, but even in shallow observation, you see like 50% of them have fairly rapid outflows, compared to low redshift, where most of them don't really have anything to detect. And a lot of them have very high velocity, that 8,000 kilometers per second thing that I showed you earlier, but there are plenty of them, a few thousand kilometers per second. This line is sort of, if you assume these things are in dark matter halo, the 10 to 12 solar masses, we'll justify that number a little bit later, then the escape velocity for these dark matter halo. Anyway, what that means is they clearly can unbind, blow up gas from the ISM. And if you look at their kinetic energy, again, coming from the scaling that we showed earlier, some of them are very, very high. They are sort of the range that I think Phil was telling us before, with few percent, 10% of the radiated energy can be coupled with these things, can blow things up. And the outflow rate, actually the mass outflow rate is higher than the star formation rate in many cases. Some of them had ALMA observation as well, in particular OH. So some of them had cold molecular gas outflow with a similar high fraction. I do think there are evidence that these quasars at very high redshift are different in the sense that they're not your normal low redshift blue quasars anymore. They're actually comparable to a population object. Some of the people in the audience know much better, the so-called extremely red quasars that are a very small fraction of quasars low redshift, but have very, very strong feedback implications in them. They seem to look like that, except these are not blue quasars, not red quasars, just your typical regular selected blue quasars. So that may be indication that they're in the blow-up phase of the quasar evolution that led to quenching. Yeah.
Plotting flow momentum against optical luminosity.
There is a momentum plot. I don't have it here, but yeah. There's a momentum plot somewhere in the paper, but they also look like just like a scattered diagram, look like this.
Kinetic energy is roughly 1%.
Yeah.
There's a lot of scatter.
It's a big scatter.
Yeah, it's a big scatter. The momentum plot also look like a big scatter, basically. All right. So let's look at an even larger scale. We finally get to the larger structure part. Yes.
About jets, do you have any low frequency radio?
So very few of them are radio loud for the sample that we have. The radio loss fraction seems to be quite low. As sort of, standard, even lower than the standard 10% that people talk about for this redshift, for these quasars we have. I believe there's one new paper that just published about the first blazar that discovered redshift 7. The blazar, in the sense they have strong variable radio and X-ray, its optical spectrum looks similar, but they're quite rare. But of course, if you got one blazar, you may wonder whether there are a lot of things people didn't find, and that's interesting. Yeah, Neda.
Quasars have these very massive black holes and are very active and quench star formation. These black holes exist today. What would be those galaxies? Would they have accreted all these extra stellar mass or factor of 10 in their present?
So yeah, I guess if there are things that blow up, then they don't have a lot of star formation anymore. They'll probably have some dry merger or something, grow a factor of a few more in their stellar mass, but not much more than that. That would be my guess. And certainly if they blow up gas, the quasar are not going to grow either. But we sort of know that. Right. So the galaxies clearly still have to grow to acquire their black hole mass, their stellar mass somehow, because we showed that at least for these objects, they're lower than the local relation. But when you blow them out, then I guess they have to grow some other way, merger or something in the lower redshift. But of course, you can blow out and re-plunge the ISM again and grow more stars or through merger. That will not prevent that, I guess. All right, so let's go to the larger scale. So of course, these quasars are some of the most extreme, rarest objects in the early universe. Roughly, people say there are 5-6 sigma peaks in the density field. So you would predict them to be the rarest and therefore most biased systems. And I think the generic prediction, all the largest structure calculations, that they're supposed to be strongly clustered. They're supposed to live in the most dense environment and highest dark matter mass in the early universe. And indeed, if you try to look at the autocorrelation function of quasars, the function of redshift, they are fairly strongly clustered. as far as you can measure, all the way reach about 5 also, and consistent with sort of dark matter halo based on their clustering properties of like 10 to the 12, 10 to the 13 solar masses. So these are massive systems, except when you go to redshift higher than 5, then the experiment becomes very, very hard because you don't have enough pairs of quasars to do the correlation function anymore. So people rely on cross correlation between quasar and galaxy. In other words, quasar is supposed to be an overdense environment to do this experiment, except pre-JWST results have been quite confusing. There are a lot of HST and ground-based observations, but they are photometric observations. You can't get the redshift, therefore your clustering signal just very weak. So I think that's about it. You just don't get enough information to measure the clustering until what is possible with JWST is because you have the ability to do spectroscopy. So this is really my favorite mode of observing now for JWST is a slitted spectroscopy mode that Aspire program, as well as a number of other programs are doing. And actually, we have the new slitless spectroscopy program called Colloquium 3D just started observing yesterday. We just have first of the 250 hours coming up yesterday, literally. And so the first Aspire program, we have 25 quasar dimensions with about 300 square arc minute of imaging. Now we're going to have a few thousand square arc minute. And this is, again, this is a dispersed object, what it look like. And the combination of JWST being super sensitive, L2 sky is really dark, and the fact that, as you've heard, galaxy formation is pretty active, more active than we thought, which means we actually got more redshift from these fields than when we wrote proposal, try to be optimistic. So we're looking for, in this region, the H-beta oxygen 3 again, but of course for galaxies. So when you subtract continuum, very easily picks things up. There's 3 dots there. You immediately know what it is, what the redshift is. And of course, with the field of this, we sort of having galaxies all over the place, regardless of redshift. We don't have any selection, obviously. So both in the foreground and in the background of the quasar. But if you plot all the galaxy redshift together, there's about almost 1,000 galaxies from these 25 fields. You will see a lot of them at the foreground, some of them in the background, or a large fraction of them piled up at what the quasar redshift is. So just by looking at the redshift histogram of this 25 quasars, you know galaxies like to stay around these quasars. Quasars are in overdense field already. This is actually our first object, the first JWST field that we had, which is one of the protoclusters. These are about 10-ish galaxies from JWST, and about a few more from ALMA, all sort of line up almost like a straight line over there, and quasar is sort of at the edge of this linear structure, very cold. There's a very, very small velocity difference among these systems. That's the things that simulation people like to tell us. They're supposed to be in this long, cold filamentary structures, high redshift, what they're called progressive overdensity. So that's the first example. And clearly, this one single field is not enough. We don't know how to extend. So we do now. This is the program that we did in cycle 2 of JWST, which we, instead of one pointing for the same field, we covered a much larger area. So it turns out this protocluster probably extends to the order of 10 megaparsec also for this particular case. So again, very cold structure over here. That's one case. Now we have 25. So 23 of them have been analyzed. These are the number of oxygen 3 emitters in each of the field. Compared to the dashed line is basically what the blank field is supposed to be. So blank field is supposed to be about 1. And some of the field have 20 galaxy-associated quasars. These means that overall quasars are indeed in overdensity environment. And the most extreme examples all look like these linear filamentary structures that simulation predicted. But again, there's a lot of diversity. Some of them very dense, 20 galaxies. Some of them not quite dense. Some of them even have no galaxy around it. So I think that indicates that quasars are really signposts of early large-scale structure growth, but not always. But finally, now we have enough sample we can actually do statistics. So the goal is to get the quasar-galaxy cross correlation because we expect the quasar-galaxy cross correlation to be geometric mean of the galaxy and quasar-quasar. And what that predicts is that if quasars are really in more massive dark matter halos than your average redshift 7 galaxies, then the quasar-galaxy cross correlation will be stronger than the galaxy-galaxy one. And we can measure both with the same data. So that's the quasar-galaxy cross correlation. That's the galaxy-galaxy one. They are indeed stronger by quite a bit. And you combine the two, you can actually now measure the correlation length fit with your correlation function and compare with simulation to get a black hole mass. Maybe get a dark matter halo mass. and the dark matter halo mass is order of a few times 10 to 12 solar masses for this particular sample of object on average. Again, there's large scatter, and we probably have interesting statistics we have to deal with in case there are a lot of scatter and how to treat them. But at least this is a strong evidence that quasar galaxies quasars are strongly clustered the epoch of reionization, and they are tracing some of the most massive dark matter halos in the early universe. I'm sure I don't remember the number, but I'm sure there's a plot showing it. Yeah, it's a big number. Even the galaxies are very, very biased, right? The quasars are sort of factor of 2 or something more biased than galaxies. All right, so we come back to the questions we raised earlier. We try to connect the different scale of physics and try to understand how high-redshift quasars evolve into the massive galaxy we see today. I want to just show some of the things that I think what's going on, what we learned from it. First, do you need massive seeds? I think the answer is yes, just because the time scale is short. But the real answer probably have to come with going to, again, lower luminosity and higher redshift from the JWST surveys that we'll be getting in the next few years and start getting now. Oops, what happened? They are certainly in mass, on average, a site of massive galaxy assembly, because you just see very high star formation rate in most of them, and they're frequent mergers. But there's a strong diversity in the sense that still 1/3 of them, we don't quite know what's going on. We do see signs of feedback in this system. They seem to be at least more common than I naively would thought, and with a wide range of feedback power, but some of them are certainly powerful enough to do damage to the galaxy. Do supermassive black holes precede galaxy assembly? I think at least for the galaxies we see, the quasars we see, maybe by construction they are, but the real situation, I believe, is much more complicated. Really need you to go to lower luminosity systems. And finally, I think this is one of the results that we really didn't think were going to work that well in terms of the JWST capability, is we really do see very strong sign of larger structure at that time around the quasars. All right, so what's next? Actually, let me just show this picture here. This is actually one system that sort of put everything together. It's one of our favorite redshift 7 quasar. It has a 10 billion solar mass black hole in the middle. It has all these weird absorption features, low ionization features, tells you they are infloating oxygen gas very close to the central engine. This is the one that is very extended in JWST and has this very strong velocity shear in element that look like rotation. And we have JWST IFU observation. You will see things coming in. This is oxygen 3 region. There are flows of stuff that coming from 10 MeV/s scale that sort of connect the quasar to the circumgalactic medium. And this object also turned out to be in the most overdense region that we know of those redshifts. We have a super narrowband imaging of this region, has like the extension of these landmark emitters associated with this quasar extend to about 50 MeV/s. So I think this is a good example of all these things finally begin to connect together. We're just in more of these examples. So what's next? I guess the next question asks how much you can push further, right? We know that quasar density drops very sharply towards high redshift. So you can ask the question, well, if we're just looking at these type 1 SDS looking luminous quasar, 10 to 9 solar mass black hole, and just extrapolating luminosity function, at one point you get one object on the sky, and then our job is done, right? So this is about redshift 9 to 10, unless quasar are doing something crazy. So I think that is the first luminous quasar that we will be looking for in the next few years, except the things are hard because quasars are getting rare, but the contaminants from either cool dwarfs, in particular compact red galaxies, are not. So it's an interesting challenge to actually how to look for them, select them, and to follow them up, because these are fairly faint objects. But of course, to look for them is really the combination of Rubin, which just started taking data, Euclid, which had been taking data for a while. I cannot show you what we have been finding, but except to say that Euclid seems to be very good. We are beginning to find quasars at interesting redshift already. And of course, Roman in a couple of years. And this is a prediction of the number of objects we can discover from combination of Rubin, Euclid, and Roman that should give you a sample of redshift between 8 or 10 luminous quasars in the coming years. Okay, so I'm going to just put on my summary slide here. I think the 3 things I learned from our early JWST observations, 3 interesting plots. One is they are site of massive galaxy assemblies. A lot of them show strong feedback, and they live in some of the earliest larger structures. Now, thank you.
So, how confident are you that the black hole mass estimate based on the width and the luminosity can be contaminated by starburst?
Contaminated by the starburst. So these are broad permitted lines in the quasar borderline region. I don't think the starburst is going to do very much. I mean, they're not. Some of them are not typically even associated with like carbon-4 or something. They're broad. They're not even associated with very much with star formation. So I think the line width is fine. The thing that you worry about are the other factors in the black hole mass measurement. One is what is the true size of the borderline region, which we do not resolve. And one of the weird thing happened recently was not weird. Interesting thing happened recently was gravity and VLT finally begin to try to resolve the borderline region with interferometry, with VLT interferometry. And the size were wrong. I mean, we're wrong. Their size probably right. The estimate was off from the scaling that we have. So that worries me. And of course, the geometry, we don't know the geometry. So whether they're face on, edge on, or whatever the orbits of whatever the configuration gases, that worries me now. So I think there are a lot of uncertainty still in the black hole mass measurement. That's why maybe we can do dynamical mass, probably not for many objects, but the gravity kind of thing will be really interesting to see what kind of black hole mass they get.
One in the
Yeah, Xiaohui, you said I love those O3 lines, and I'm just curious, is there really no SED differences for the things with the super broad lines? I mean, are they either redder in the rest frame optical, redder in the MIRI?
So I guess the data are still coming in. We just plot the simplest, like one color. I don't think there's a trend, but we could try to fit more when we get all the data. These are things that are sort of start still being collected, but it's not obvious at least.
Do any of these have X-ray? I bet that's very hard.
I have not correlated the property with X-rays. I probably should. Not all of them, a good fraction of them do. I mean, especially, we have been following up these X-ray sources. I mean, these sources in X-ray quite diligently in the last, and we means the border community for the last few years. I think most of the object redshift, maybe half of the object redshift higher than 6.5 also has some X-ray observations. Not all of them detected, many of them are. So we probably should do that. Thank you for telling me that. Yeah.
first in the front and then Jeremy.
Thank you for the great talk and great results. One of the predictions of the population 3.1 model that we're working on, which also produces massive seeds, but is different from direct collapse, is that these objects should be born alone and be isolated and basically not have another AGN within 2 or 3 co-moving megaparsecs. So I guess, is there any evidence for secondary AGN in the surroundings, and what kind of mass dark matter halos are present as secondary halos around?
So I think for old object I'm aware of at redshift higher than 5.5 or so, there's one object that has a very marginal X-ray detection as a companion within a couple arc seconds or something, and we were trying to get a better spectrum for Chandra for years now. We just couldn't. So there's a question mark there. That's only one that I know of that may have about this luminous quasar. This particular population may have a AGN companion. All the other things, we now have all these JWST observations. If they have a broad line, we will see it, because a lot of them are IFU stuff. I don't think there's any sort of strong broad line AGN to speak of. Of course, they can be obscured, because you see plenty of them are in massive system with companions. Whether they have hidden AGN, that's part that I don't know.
You mentioned very early on when you were showing one of your stacks of spectra that showing the silicon-4 and carbon-4 lines, that it looks like these quasars were enriched very early. Can you make that at all quantitative? I mean, is there any trend in say, the equivalent widths of those emission lines with redshift?
Yeah.
Metallicity variation.
So it's on this plot, right?
I mean, I guess I'm asking, is there any reason to think that the highest redshift quasars are less enriched than the more recent ones?
I mean, from this spectrum, I don't see any trend about with redshift. But of course, these are broad lines, so they are really close. They probably don't have any particular implication to the whole galaxy.
Be my follow-up question.
Right. So in order to get real metallicity measurement of these host galaxies, I think we need even deeper IFU than now we see oxygen strait. We need a BPT kind of thing or whatever. We need oxygen 2 or something to get some estimate of metallicity. It's harder.
Just a question back on the question with estimating the mass from the growth lines. What happens when there is like a lot of obscuration? For example, in the mergers, can we still have a good estimate of the black hole mass if we know there's dust extinction, and so it's going to affect the
these quasars are not obviously distinct. They have very blue continuum. So I think from that obscuration part is okay. So I mean, they don't have obvious dust in front. Some of them do, but most of them are just like your typical SED of low redshift quasars extend to whatever the wavelengths we can cover.
I was going to follow up with a question that Jeremy asked. Some of these objects show unusually strong iron 2 emission.
Yeah.
I mean that now one of the spectra that you flashed was an example of that, but they do seem stronger than lower redshift. Goes in the opposite sense of what Jeremy was asking for. Can you comment on that?
Iron 2 measurement we had so far, I mean, the JWST one, we haven't done that. So in the resonant optical region, there have been resonant UV, around magnesium 2, there are a lot of iron 2 as well. For that measurement, I think statistically, they're about the same. There must be somewhere there's a plot of magnesium 2, iron versus magnesium ratio, the function of redshift, they seem to be fine. They seem to just like the same kind of large scatter, but there's no obvious trend towards redshift 7 also. I think that's what. Some of them do look weird, yeah. Yeah.
More objects on the extreme, yeah.
Can you say anything about in terms of the early enrichment, the ratio of silicon to carbon from the ratio of those?
Right, you can. And they don't seem to change from lower redshift. And you can do cloudy or something. You want to measure the metallicity. People have done that for years, and they seem to be quote unquote super solar. But then you worry about saturation and everything else. But they don't seem to change, as far as I can tell.
Is the estimated abundance of this 10 to the 9 solar mass black hole consistent with what we see today after adding expected evolution, mergers, and accretion?
So I think a lot of the theoretical models are sort of calibrated from the quasar observation. So maybe by construction, they're okay. But exactly whether they're consistent off the stream system, I don't know. Because I mean, as I said, many of the simulations sort of try to reconstruct to get the number density to be more or less consistent and high redshift as well. So I'm not surprised by the number density, I guess.
Was there a question in the back? Okay, no.
To later.
Oh, yeah, go ahead.
No. I'm saying I'll speak with Jerry later. It's fine.
Okay.
If you plot the distribution of Eddington ratios, do you see a feature that suggests the Eddington limit is happening, or put it another way, what is the best evidence for super Eddington accretion that you have?
This is a figure, right? This is the Eddington ratio. I mean, so whether these are true Eddington ratio or not, you can argue whether, I mean, like things really trap and whatever, they are funny models. There's one anecdote evidence that I think you have to somehow believe these are, this ratio means something, is that we have two examples of objects that are way off from this from this relation. That when we discovered it, both of them were lengths. So basically, when we look at this, oh, this is all from Eddington. Maybe the luminosity is not real. Remember, this relation sort of has a L to the square root of L building into how this plot is constructed. So if your luminosity is off, then you get out of the relation. So that's an anecdote that I know that both the cases were like, this is so off by a factor of 3 or 4 from this plot. Most of them don't. They're like here. Then we follow them up. They're both lenses.
So we've already talked about and had many interesting questions and discussions. Let's